I'm Hal Schenck from Auburn University, who will talk about the stuff in the title.
I don't know if I'm going to talk after that. That was not a ringing endorsement. The stuff in the title, man. Jeez. The first thing I want to say, so this is the avuncular advice for the young people. This is a project that is about dynamical systems, and dynamical systems are pretty far out of my wheelhouse. But this is part of sort of the joy of mathematics is going to a talk and thinking, I wonder if some sort of piece of some tool that's in my toolkit could be applied to this problem. And that turns out to be the case. So it's going to be, I think, there'll be the first half of the talk will be mostly sort of background and setup of the problem. The reason for this talk to appear in a combinatorics and geometry seminar is that the underlying data structure is going to be a simple graph. So underlying everything we do, there's going to be a simple graph. And the geometry is that we're going to translate a problem from dynamical systems into algebraic geometry, not super high power algebraic geometry, but very concrete questions about quadratic equations. So that's the background. And I want to start out with a video. So despite the Fireflies in the title, which appear in a Scientific American article over 50 years ago on synchronization. So sometimes a swarm of fireflies, which is everyone's sort of marching to the beat of their own drum, flashing sort of sporadically, and sometimes spontaneously it synchronizes. So you can find videos of this on the web. They're not so great, but this is a really nice video from the UCLA math department on synchronization. So let's see, and let me get to full screen. So here it is. So, uh-oh, that's not good.
You're sharing the wrong window, I think.
Am I sharing the wrong window? Let's try it again. Let me just do. Let's do that. So, well, we can hear them synchronizing. I've never seen this happen before. What do you guys think? Well, maybe we'll return to it. You can't see this. You can't see oscillators on your end, right? Yeah, okay. Okay, well, we'll leave it in small instead of trying to go to full screen. So here's a system of 5 oscillators. What the heck? I'm not touching anything anymore. Okay, so these are 5 oscillators. This is the underlying data structure here is actually a complete graph. So, and the reason it's a complete graph is, as you can see, there's a platform that's supported on 2 cans. And what that means is every one of these oscillators is influencing the others. So there's a complete graph on a K5 that's actually underlying this. And as you can see, the oscillators started out completely unsynchronized, and now they're sort of slowly, it still doesn't look like they're getting.
Oh, I'm only seeing the title page.
Oh,
Yeah,
no.
we're not
I'm
seeing
not.
any of your share.
Oh, okay. Well, I'm going to skip it then, and we're going to go back to where we were. So let me go back to the presentation.
We've all copied down the link, so we'll watch it on our own.
Good. Okay. Okay. So the oscillators. The point is that now what the heck's going on? It's not letting me advance my screen. Oh, there we go. Okay. So what's the point of this? Oh, I should have said at the beginning, this is joint work with Heather Harrington, who's a dynamical systems and applied math person, and Mike Stillman at Cornell. So why are we interested in oscillators despite the failure of my technology there? That shouldn't turn you off because they appear all over the place in applied mathematics. So there's a list of them here on the screen: the biological chemical networks, power grids, neuroscience, wireless communications, and many other applications. Heather, actually, part of the connection here is that Heather does a lot of work in neuroscience, and so these oscillatory systems are of interest there. So the system that we're going to study, this is going to be a system of first order ODEs, and they're going to be trigonometric. And this was proposed over 50 years ago by Kuramoto. And the ingredients, like I said before, so we're going to have a simple graph on n vertices. And the picture that you want to have is that each of those vertices has an oscillator, and that oscillator is going to be emitting a periodic signal. We're going to model that with a an angle between 0 and 2 pi. That angle is a function of time. So as time progresses, we're emitting a periodic signal. So those are the oscillators. And then for notation, I'm going to let G sub I be the set of vertices adjacent to vertex I. So not every vertex can see each other. Unfortunately, well, in the video, none of the vertices saw each other because we couldn't see the video. But you could imagine in a complete graph, that's where every firefly or every oscillator can see every other oscillator, but that would be atypical to have that kind of behavior. So the interest is in the behavior of this dynamical system and the relation to the combinatorics of the graph. So here's the actual system of ODEs. So theta is the angle at vertex I, and theta is a function of time. And then the differential equation is here. So theta I prime is omega I plus summation kij times some sign. So let's see what these things are. So the omega I is what's called the natural frequency. So if you take a tuning fork and you smack it against your desk, it will vibrate at a frequency. That's the natural frequency. The kij's are the strength of the connection between vertex I and vertex j. So if vertex I and vertex j, if those oscillators are not influencing other, kij will be 0. And otherwise, kij is some weight that reflects the strength of the connection. And then we have this mysterious sign of theta j minus theta I. So I want to say sort of what this system is representing, roughly speaking. And this is a loose analogy, but it's not so bad. So suppose that you have a bunch of runners that are moving around a track. And not every runner can see everybody else. It's a big track. But what happens is if you can see someone in front of you, so these are going to be sort of friendly runners. So if you see someone in front, you're trying to speed up and group it up and catch them. And maybe because it's nice runners, if you actually turn your head and see somebody behind, maybe you slow down a little bit. So the question is, so this is what this system of differential equations models, is that kind of behavior. And the question that we're interested in, the behavior that, or the dynamical systems people are often interested in, is synchronization. When these oscillators that are all operating at different frequencies suddenly begin to harmonize and operate in unison. Okay, so I mentioned what this original equation is up here, but we're going to study a simplification of this. And the simplification is to assume that all the oscillators are identical. And that lets us wipe out this omega I, the natural frequency, because the natural frequencies are all the same. And then the rather drastic simplification is to assume that the strengths of the connections are all either a 0 or a 1. So in this kij here, because these kij's are for notice this j is in g sub I, so the only things that are appearing in this differential equation at vertex I, it's only influenced by the behavior of the adjacent vertices, the vertices which can actually see it. But nevertheless, assuming these weights are all 1, that really simplifies this system of equations to this theta I prime is this summation j and gi of sine theta j minus theta I. So this seems a pretty straightforward system. I mean, we could actually give this to students in linear algebra when we teach them about how to solve systems of linear systems of ODEs, right? So nevertheless, it's extremely popular. So if you Google it, this morning I got 3.6 million hits in Google for Kuramoto model. And you might say very reasonably, Google overcounts everything. But if you go to MathSciNet and you check for Kuramoto model, you'll still get about 2,000 hits. So it's an extremely well-studied model. And I want to talk a little bit about, I'm not advancing again. This is not. Don't know what's going on. Okay, I'll do it that way. Okay. All right, so definitions. So these are a set of angles. So if I pin my angles to certain things, so these theta I stars are actually numbers now. I've specialized some t. We say that system of angles is a solution if it solves our system of differential equations. So when I set theta I prime to 0, and these theta I stars are actual angles, I solve this system of differential equations. So this is called a solution. Now, we're not going to be interested in dynamical systems. When you look at videos, a lot of times there's little particles orbiting things. And so having a solution is not good enough. We're going to be interested in stable solutions. So that's going to be solutions where once we get there, we're kind of stuck. And I want to, there's some formal language that I'll introduce now here. So the all-in phase solution is a very simple solution if the theta I stars are all equal. So this is exactly the synchronizing solution where all the angles are the same. That means everything is flashing in unison. And that obviously solves the system because sine of 0 is 0. So if the theta I stars are all equal, we solve the system. But there's some other solutions that are called standard solutions. So because sine of 0 and sine of pi are both 0, anytime that the differences of the angles are 0 and pi, those are called standard solutions. So these are sort of, again, things that just we don't have to do any analysis at all. And so the interesting thing, and where the dynamical systems come in, is my third bullet point here, which says a solution is a stable solution if we take a small neighborhood of that point. Remember, these solutions, the theta I stars are an actual point, and we take a small neighborhood around it and let time evolve forward. And as time evolves forward, if I was any other point in that little neighborhood, I get sort of sucked in to the solution P. So this is, again, we're evolving our system in time. I have a small ball around a solution, and if I'm anywhere in that neighborhood, I'm sucked back into this tiny black hole, so to speak, at the point P. So that's called a stable solution. And then the definition of synchronization is if the only stable solutions are the all-in phase solutions, when everything is synchronized. So those are the definitions that we're going to need. And the first observation is that this system has a very specific form. So this is what's called a gradient system. So our theta I primes, those derivatives are the gradients of the system of capital F, where these are the cosines, right? Derivative of our cosines are the sines with an appropriate sign, with that minus sign introduced. And so what does this mean? So this is sort of dynamical systems language. This is what's called a dissipative system. And the point is that there's energy leakage. So if you take a toy model of some system where you've got kinetic and potential energy, say a little race car on a toy racetrack, it starts off at a peak, and you let it there. It's got high potential energy, zero kinetic energy. It starts going down down a slope. The kinetic energy increases, potential energy decreases. It hits the bottom of a little valley and starts up the other side. But then it's going to go back and forth and back and forth. Eventually, because the system's dissipative, it gets stuck at the bottom of a valley. And so this is a dynamical system of that type. And that certainly doesn't speak to me as an algebraic geometer or commutative algebraist, but what it speaks to in dynamical systems language is that it's the nicest sort of dynamical system. And this means that there's no limit cycle. So what's a limit cycle? A limit cycle is when you look at these dynamical systems videos where a point doesn't converge to, you don't have you have some orbit. So a point is orbiting some sort of some sort of an attractor, right? So that's a limit cycle. So we don't have positive dimensional stable solutions is the point. All our solutions are going to be little sinkhole points. The other thing is that we also don't have chaos. So chaos is the butterfly effect, which means that this system is very sensitive to the initial state. And so again, this is the butterfly effect is, right, if a butterfly flaps its wing in Hong Kong, there's, I don't know, let's see, we're BLT, so Baton Rouge, Toronto, and London. So in London, suddenly it starts to snow. Well, it might have started to snow. It might even have snowed in Baton Rouge, right? So there's no chaos in the system. And so the punchline is that for this system, as time evolves, these paths will converge to points. Okay, so that's sort of more dynamical systems background. And so now what we had is there were two things we needed. We needed to solve the system. We needed to have our the theta I primes were 0, but we also wanted the solution to be stable, which meant that if we perturb that solution a little bit, and let time evolve, we were sucked back into the point. And so what's great about this is that this test is not, and this is not for all derivatives, but we can approximate stability with something called linear stability. And so this is basically the Hessian test. So I want to do, again, a loose analogy, but pretty accurate. In Calc 3, when we teach our students about what is a point, a minimum or a maximum on a surface, they take the Hessian, right? And then they compute the Hessian, the determinant of the Hessian. And if it's positive, they know it's a min or a max. If it's negative, it's a negative, it's a saddle point. If it's 0, they don't know what's going on, right? So that's our Hessian test. And roughly speaking, for stability, what we're going to do is we're going to take the Jacobian matrix of our system of sines and cosines. Well, that Jacobian matrix is going to be a bunch of cosines. And then look at the, it's not the determinant because we have a lot more than 2 equations like we would have in Calc 3, but it's exactly analogous to that. And so we're going to say that a point is stable or linear. This is actually linearly stable if we have, so the Jacobian is going to turn out to be a symmetric matrix. And if it has always will have 1, 0 eigenvalue. If all the other eigenvalues are negative, that's going to be called a linearly stable point. And that's exactly the analog of being a min of your function in Calc 3. Now, you can be stable without being linearly stable. And the analogy here is that in Calc 3 for the Hessian test, if you're 0, you don't know whether you were a min or a max, right? You have to look at higher order derivatives. And so that's exactly what we're going to do here. We're going to do an approximation by just looking at the first derivatives of this system. If you end up with too many 0 eigenvalues, you don't know if you've got a stable solution. And then what you have to do look at higher derivatives. And that turns out to be computationally very, 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 very time consuming. So what we're going to do is only look at sort of the Hessian test, and we'll call a system that has, when we plug in our point, we found a solution. So theta I primes are all 0. We then plug that point into our Jacobian matrix. If we have all but 1 eigenvalue negative, that's going to be called a linearly stable solution. And so linearly stable does imply stable, but the converse is not true, as I mentioned. So you could be a stable solution, but maybe you have too many 0 eigenvalues. So this is our first approximation to solving this stability question, is to look for linearly stable solutions. And at the bottom of the slide, you can see it says, we might need, if we have too many 0 eigenvalues, we might have to look at higher derivatives. So it's always good to have a toy example on the board. So here's our toy example. This is a pretty innocuous system. So we've got 5 vertices, 6 edges. And our system of equations is up here at the top. So our theta I primes are all 0, and those are our sums of sines. So you can see at vertex 0, at this bottom vertex, I'm adjacent to vertices 2, 3, and 4. So I need sine of theta 2 minus theta 0 plus sine of theta 3 minus theta 0 plus sine of theta 4 minus theta 0 to all be equal to 0. And so on for these equations. So now when we take the Jacobian of this system of equations, what I get is this 5 by 5 matrix down here. And I want to go through this slowly. And I want to ignore the diagonal for a second. And what I'm doing, so let's take this first equation. I differentiate it with respect to theta 0, then with respect to theta 1, then with respect to theta 2, then with respect to theta 3, then with respect to theta 4. So visibly, if I differentiate this with respect to theta 1, there are no theta 1s in this first equation, and so I have a 0 in row 1, column 2. When I differentiate this with respect to theta 2, well, there's only one of these signs that has a theta 2 in it. Derivative of sine theta 2 minus theta 0 is just cosine theta 2 minus theta 0. So in row 1, column 3, I have that cosine, and so on across the rest of the way. Now, the diagonal entries, those little asterisks, which are there because I can't fit a minus, or I can't, in an aesthetically pleasing manner, fit a minus sum of negatives in there. It's just the negative sum of the other entries in that row, and it's because when we differentiate, for example, that first equation with respect to theta 0, I get all those 3 signs, but they're turned into cosines, and because my theta 0 has a negative, I've got a negative there. And this immediately tells us why we have a 0 eigenvalue, because visibly our rows sum to 0, right? So we can easily see that all the rows sum to 0. And so what we're interested in, again, to recap, we want to, number 1, find angles that satisfy this system of equations at the top half of the slide. And then I'm going to plug those values into my Jacobian matrix and see if I have all negative eigenvalues at that solution, right? And if I do, then I have all but one, sorry, as 1, 0 eigenvalue, all other eigenvalues negative, and see what I've got. So that, and if I have all negative ones, that's a stable solution. So again, continuing with our sanity check, let's do this for the all in phase solution, right? So the all in phase solution, all the thetas were equal. We know that's a solution, right? And so in the top matrix, of course, I get zeros on the right-hand side. In this bottom matrix, I'm pretty happy because cosine of 0 is 1. And then on the diagonal, I have a minus the sum of that. So what I'm going to get here at the all in phase solution is this matrix. And so now, grad students, even though we're virtual, at some point, I'm sure our paths will cross. So this is Hal's usual audience participation prize. So a beer, or for the teetotalers in the audience, an espresso or a non-alcoholic beverage for the first grad student to recognize this. So what is it? Somebody's got to shout it out. I'll open it to faculty if grad students are not going to avail themselves of the opportunity for a free beer. I will tell your advisor. In fact, if you don't avail yourselves of the opportunity for a free beer, I will email everybody's advisor and say, hey, you should cut this student's stipend.
Laplacian.
I heard it, Laplacian. That's almost right. It's actually the negative of the Laplacian, right? So this is the negative because we got minuses on the diagonal. So this is the negative of the graph Laplacian, which is, I think, the Laplacian is ubiquitous, right? It appears in differential geometry, and it appears in graph theory. It appears in solving if you solve the heat equation on a graph, all you're doing is solving the Laplacian, right? So I think this is really cool and a nice connection. And so our question is, when does our, so it's automatic, right? We know that this is a standard sort of, I guess, exercise in maybe first semester differential equations, that the Laplacian itself, this is the negative, but the Laplacian is positive semi-definite, has 1, 0 eigenvalue. And so, so these are the point. What's the point of that? Well, here, it's easy to check because it's the negative of the Laplacian. Indeed, then we have all but one eigenvalue negative. And so the all in phase solution is indeed a linearly stable solution, and hence a stable solution. So this was sort of a long-winded sanity check, but at least we see that this all in phase solution is a stable solution. All right.
Can I interrupt, Hal, and ask, how about those standard solutions? Does that come out nice here too?
It's a great question. So Graham's question was about, and maybe I'd buy Graham a beer too for asking a question, because my metric for a talk is always questions are a good thing. So those turn out, they're always solutions, but not a single one of them is going to be a stable solution. And what's going to be kind of crazy is that those things, all those other solutions, are going to appear to sitting on the Segre. They're going to be on the Segre variety, the Segre surface of P1, actually Segre n-fold corresponding to an embedding of P1 cross Pn minus 1, which is, I find pretty amazing and pretty cool. Anyhow, so, but we'll come to that later. We haven't gotten to, if you're sort of thinking, where is the algebra or the geometry in this? Right now, this seems rather far afield, but we're going to get there very soon. I'm not sure if it's the next slide, but it's coming up. Okay. So one thing I want to mention is, so there are interesting stable solutions that are not all in phase. And so the all in phase is when everything is flashing at the same time. There's another thing, or a common, it's called exotic, but there's stable points that are not all in phase. And the example is if you have just a cycle, what you can have a stable solution, and what happens on the cycle, it's like the wave at a sporting event, where it's sort of a periodic wave that's cycling around. So there is how to say it, there is some sort of harmonization, but it's not where everything is occurring at the same time. It's this sort of periodic behavior. And so this is actually going to turn out to be what we're going to be more focused on, is this existence of exotic solutions that are not synchronizing. So again, I have this little blurb that says, think of an audience doing a rotating wave at a football match. So back to the synchronization question. It's known that all trees synchronize. About 30 years ago, Watanabe and Strogatz showed that a complete graph synchronizes. And it's also known that all cycles of length greater than or equal to 5 have exotic solutions. And so the question that we're going to focus on is which graphs have linearly stable exotic solutions and which graphs synchronize. And I also have not talked at all about history. I said there's about 2,000 papers on MathSciNet. So this is, I think, almost our last page of dynamical systems background. So the connectivity of a graph is just the minimum over all vertices of the degree of a vertex. That's the number of edges which are adjacent to that vertex, divided by n minus 1. N is the total number of vertices. So in particular, a complete graph will have connectivity 1 because every vertex is connected to n minus 1 other vertices. A cycle, this is not, I was going to say for another beer prize, but it's too easy. A cycle, obviously, each vertex has valence 2, so the connectivity of a cycle is pretty low. It's 2 over n. So as n gets very large, cycles have a very, very, very low connectivity. All right. So the research in dynamical systems has indicated that when a graph has high connectivity, you have synchronization. And remember, synchronization says that the only stable solution is this all-in-phase solution when all the angles are equal. So I think the first interesting result, this is almost, notice, this is about 15 years after Strogatz and Watanabe's result. If you have connectivity 0.9375, you get synchronization. And then there's a vast improvement about 7 years ago by Ling, Zhu, and Bandiera, who improved this. This is in Siam Journal of Optimization. They're using techniques from optimization to bring this down to 0.79. And then I have a result that just shows that that even marginal improvements in this result are interesting. So 2 years later, Liu and Steinerberger bring this down by what? By about 0.004. And so the question is, we're bringing the connectivity down. On the other hand, it turns out there's examples of graphs with pretty high connectivity, not as high as this, where you don't have synchronization, where you have these exotic solutions, and there you have connectivity 0.68 or so. And so the question that we were attacking when we first looked at the problem was either to find more examples of exotic graphs and bring this threshold up above 0.68, or to bring the upper bound down from 0.78, right? So there's this interesting range of about between 0.68 and 0.78 where it's not clear what's going on. So there's a theorem. This is bad. This S is Stillman, not Schenck. So there's a result of Strogatz, Townsend, Steve, of course, is dynamical systems. Alex Townsend is a numerical analyst, and the last S is Stillman, who's an algebraic geometer. So they find graphs with high connectivity that's low, but it's getting very close to 0.75 that have equilibria with negative definite Jacobian, but they have extra zero eigenvalues. So this is not going to be linearly stable. It looks like they're stable, but they can't verify it. So it looks like there's some threshold for synchronization, which is 0.75. Now, the natural question is, what's the is there some theoretical reason for this? No, the answer for why this conjecture is that connectivity 0.75 is the threshold for synchronization is lots of numerical computations. So, but still, that's a rather appealing, I mean, there's got to be some really, really cute theoretical reason for this to be the threshold, but that's the conjecture. And this is the thing that we're interested in studying. So before I reset and do the sort of geometry or geometry and algebra, these are the questions. So first, understand for a particular graph if the system synchronizes. If not, that means there's exotic solutions. And then actually we'd like to create, as we always do in sort of computational math, create a zoo of examples. And we're going to use the naughty graphs package to do that, to analyze graphs of small size and understand what the behavior is, and to try for a given graph to understand this set of equilibrium solutions. And so the standard approach here is using dynamical systems and numerical analysis. And so it turns out that the problem is that you can actually, the fact that your solutions are points means whatever numerical analysis you're doing, finding a specific point is going to be like finding a needle in a haystack, especially if it had, so what's that little basin of attraction where you get sucked, the mini black hole is called the sink basin. And if the sink basin is small, if you have a very small neighborhood of the point where you get sucked in, that's going to be extremely hard to detect computationally, and it has happened in practice. And so this is now the end of the background, and now we're headed for algebra. And so let's do the algebra. And this is really, really simple. So what are we going to do? We're going to let xi's be cosines, yi be sines, and then we use our happy trig identity that, you know, sine of a minus b is whatever. I always get it backwards, but sine a cosine b minus cosine a sine b, or the negative thereof, but it is what it is. And so we have this system. Notice now, with n vertices, we now have two n equations because we've introduced, at each vertex, we've introduced two variables, the x's and y's. Of course, we have our standard trigonometric equations at each vertex, which are sort of giving us these cylinders, right? At each vertex, we have the equation xi squared plus y squared equals 1. So we have these sort of cylinders in our 2n dimensional space. And then we also have these n lovely quadratic equations. Fi is the sum of xi yj minus xj yi's overall. And we have one of those equations, one quadratic for each vertex. So we have 2n quadratic equations. Notice they're affine equations because we have these ones in 2n variables. Now, and so when we're looking for equilibria, this has not gotten to the Jacobian matrix at all. Just to find solutions, we have to solve these 2n equations. Now, the problem, or the fly in the ointment, is that, so here's, for our running example, these are the quadrics. And what we're going to concentrate on in the remainder of this talk is I'm going to kind of ignore for the time being these cylinders, the xi squared plus y squared minus 1, and focus on this quadratic ideal that is determined by the graph. So I have it for our example here. We have these 5 quadratic equations. Now, the problem is that these polynomials sum to 0. That's an easy consequence of our original matrix. And so our putative 2n equations and 2n unknowns has suddenly turned into 2n minus 1 equations and 2n unknowns. Well, I'm never going to have 0-dimensional solutions, right? I have too few equations to cut me down. And so the happy thing is that those other equations, the xi squared minus yi squared equals 1, those are affine equations. And we can always tune our parameters so that the angle at one vertex starts out as 0, right? So I'm going to pin one variable, one theta I to be 0. When I do that, I lose the xi squared, x0 squared plus x0 squared plus y0 squared equals 1. So I lose one equation and I lose two variables. And so by pinning, specializing the value at one vertex, I'm now in the situation of 2n minus 2 equations in 2n minus 2 unknowns. And so you can now hope for solutions there. And of course, it's easy to see that the xi squared minus yi squareds equal to 1 are a complete intersection. They're in disjoint sets of variables. So all the action is occurring in this system of n minus 1 quadratic equations. And so that's where we're going now. And this is, of course, happy commutative algebra land. So we've got these equations. And so the first observation, which in a sense is very pedestrian, but it took us an embarrassingly long amount of time to see it, is that we have these sine theta j minus theta I are little determinants. And so in particular, at each of these quadratic equations that we get at a vertex is a sum of determinants. But remember, the j is dynamic. The j is ranging over all the vertices adjacent to vertex I. Vertex I is pinned. And so we have this system at each vertex, we have a little 2x2 determinant, which is on the one column is just the variables for the vertices, and the other is the sum of all the variables adjacent to that vertex. So that exclamation point perhaps is reflecting our surprise when we realized that we were looking at a bunch of determinantal equations. All right, so what? So if we recast this as a system of determinantal equations, those 5 quadrics on the previous page can be expressed this way. And we immediately see, I want to do a primary decomposition of this ideal. I'd like to find the components of the solution set, right? So we're going to decompose our quadratic ideal. And one thing that's easy to see that jumps out at us here is when we've written things in this fashion as determinants, is that if the x0 plus x1 vanishes and y0 plus y1 vanishes, that's 2 conditions, that causes the vanishing of these bottom three polynomials. But also you can see that we could combine the top two determinants into something that does have also an x0 plus x1 in a column and a y0 plus y1. So in fact, it turns out that there's that component, we can see that if I let x0 plus x1 vanish, y0 plus y1 vanish, and then take one remaining quadratic, this is a set of solutions in the quadratics coming from the graph. This is visibly a codimension 3 ideal. And now remember, we were in 5 vertices, but we dropped that down to, so 5 vertices, but then we dropped to 4 vertices. So we're in 8 variables. This system of equations is codimension 3. And so this is going to have a positive, this locus, even after I toss in my other quadratic equations, this is going to have a positive dimensional solution set. And in fact, that's going to cause us to for it to be impossible to be linearly stable. And now I realize that things are moving a little fast. And what's happening here, what's really beautiful is if you think about it, going back to the Jacobian matrix, what does the Jacobian matrix represent if we had a system of equations? Well, the kernel of the Jacobian is the tangent space to the solution set, right? And so when I have too many 0 eigenvalues, that's going to say that my tangent space, if I have 2 or more 0 eigenvalues, that's going to say that my solution space is of positive dimension, right? Because the tangent space is positive dimension, or I'm at a singular point. And so the upshot is that the equations that we have in terms of the Jacobian matrix tell us about dimension of tangent space. And so because this component here at the bottom of the page is visibly a positive dimensional thing, that tells us without even looking at the Jacobian that there's going to be some piece of the solution set that we can throw out because it can't be linearly stable. And if it can't be linearly stable, it's actually easy to show that well, we could have extra zeros, but linear stability implies stability. The converse isn't true. But it turns out that if we analyze it, because it's a positive dimensional solution set, that would mean that a point, if you had a solution on there, it can actually move. And if it can move, that means that it's not a 0-dimensional solution because it'll have a positive dimensional sink basin. Anyhow, the point of this whole analysis, which went fast, of this little graph is that the combinatorics of the graph tell you about the geometry of the solution set. And so there's a little tiny primer here, which I'm not going to go through in detail. This is for sort of non-algebraic geometers about the translation between the primary decomposition of an ideal and the geometry of the set of solutions. So once you have a primary decomposition of an ideal, then you have a decomposition of the solution set into irreducible components. And so I had a toy example here. And the point at the bottom of this page is when we're looking for 0-dimensional solutions, we actually need to be, because of the number of equations, we're looking for components in our solution set which are complete intersections. So we have to have each one of those FIs is chopping our dimension down by a certain amount.
Hey, Hal, can I interrupt a second and ask what happened to the signature requirement on that Jacobian? Somehow that's
Yeah, I totally ignored that. So good question. So Graham's signature requirement on the Jacobian. Right now, all I'm looking for are components in my solution set that I can dispense with because I have too many zeros. And that means if I have too many zeros on so basically here, I'm sort of going backwards. What I was saying is here in the primary decomposition, we find a component that is positive dimension. If it's positive dimension, it's going to have a positive dimensional tangent space. And when you sort of reverse engineer and go back to the Jacobian, that's going to mean the Jacobian has too many 0 eigenvalues. And so we can dispense with it in the hunt for linearly stable solutions. But more than that, you'd say, well, that was linear stability, but you already told us you could be stable without being linearly stable, right? But the point here is that if I'm a positive dimensional solution set, that means actually that I could move on it. That means I don't have a 0-dimensional sink, right? I actually have this big black hole that's a positive dimensional black hole, and that's impossible for this kind of solution. So Having a positive dimensional component means we can just forget about it and throw it out. Why do we care about this? When we're searching for solutions, this means we can narrow our solution space by doing a primary decomposition of this ideal that we got from the graph, right? So that's sort of the raison d'etre here. So we did that complete intersection. And so now this is the Segre variety. So I have about 3 minutes left. But the Segre variety, remember we had these determinal equations. And so the Segre variety is in this case, we're doing the Segre variety for P1 cross a Pn minus 1. And so if I do the Segre variety for P1 cross Pn minus 1, that's given by the 2 by 2 minors of a 2 by n matrix, which I've exhibited here. So this was, this is one of the oldest varieties in the book. So if you were, pick up Joe Harris's book on algebraic geometry or something, the Segre variety and Veronese variety are some of the first classical varieties one studies. Segre variety is not a complete intersection and has dimension n plus 1. So what? So for our particular toy example, this is the primary decomposition. For our little toy example, here's the primary decomposition. We have two ideals, an I1, this is the one we saw before. Another ideal, which I've written I2, this is codimension 4. And so these, when we couple this I2 with those cylindrical solutions, we will get zero-dimensional solutions out of I2. But then we have a third component, which is sigma. I haven't written it down here. That's the Segre variety. And it turns out one can prove, and it's actually a proof that is interesting because it involves counting dimensions of tangent spaces, and then the graph Laplacian actually pops up again because the graph Laplacian turns out to be encoding the tangent. It's the tangent space at a particular point, and the particular point is the all-in-phase solution. And so the proof that the Segre, the ideal of the Segre variety is always a minimal prime of this graph ideal involves some particularly nice geometry. And so what's the situation down here? It turns out that this x1 has, as I said, dimension 7. And so when we add in our the other equations, we can't have zero-dimensional solutions. We can have zero-dimensional solutions on this x2 component and on the Segre variety, but it turns out that on the Segre variety, those are not linearly stable. And so that's sort of the end of the theoretical portion. There's two theorems here. One of them is the first one that I mentioned about the Segre variety putting in an appearance. The second one is basically this is not interesting until one starts to identify the graphs or subgraphs that give rise to exotic solutions, and we do that. But what I want to do is conclude with a few pictures. I'm now over time, but I'm going to go 1 minute over. So this is an advertisement for the Naughty Graphs package. So there's a great package called Naughty Graphs that you can easily say, give me all simple connected graphs up to automorphism. This is the key, right? So up to automorphism on a certain number of vertices. And so if you do that, we did this analysis, and the stumbling or the bottleneck here is actually the numerical algebraic geometry that goes into the computing the eigenvalues of the Jacobian matrix, because now you're doing real algebraic geometry. And so that's where it slows down. But we did analyze all simple and connected. Your graph's connected. If the graphs aren't connected, the oscillator systems are disjoint. They don't care about each other. And so we did this analysis. So here's the ones on 5 or 6 vertices. On 5 vertices, there's only 11 isomorphism classes of graphs that are connected. We're ignoring also cases where there's a dangling vertex, because that vertex is only influenced by the behavior of the vertex it can see. So we want 2 graphs to be 2 connected. On 6 vertices, there's 2 examples of graphs with exotic solutions. There's 61 isomorphism classes. So you're saying, so what? Things get a little more interesting with 7 vertices. There's 507 isomorphism classes. These are the set of everything with 7 vertices. And you immediately start, of exotic solutions. And you immediately look at this and say, well, there's obviously a theorem here which says that I have an induced 5 or greater cycle, right? Everything, it stares us in the face, right? I got a 5 cycle, a 6 cycle, or a 7 cycle. So then you might say, well, there's the conjecture. And now you go to 8 vertices, and you can still do this computationally. So on 8 vertices, there's something like 7,500 isomorphism classes. There's 81 of them that have exotic solutions. And in fact, yes, the conjecture that we had about having an induced cycle is correct. Oh, except thank God for computations, except for one. So there's this graph on 8 vertices has an exotic solution, and it doesn't have an induced 5 cycle. And so the next step, unfortunately, when we pass to 9 vertices, there's about 200,000 isomorphism classes, which is not a daunting number computationally, except that the numerical algebraic geometry and identifying the eigenvalues becomes problematic. And so there's ongoing work that we're doing, which surprisingly involves the matrix tree theorem in algebraic geometry. But I will stop here because I'm already a couple minutes over and say thanks for your attention. And I owe somebody, I don't know who it was, a beer or an espresso. So thanks. I think I have a thanks. Thanks.
And just for the record, Hal, you still got 3 minutes if you want to squeeze in.
All right. So what I'd say is, so going back, so what our goal is to get a complete combinatorial description of the primary decomposition, right? This is, and you think, okay, how hard could this be? I've got a graph. From the graph, I produce a quadratic ideal. A quadratic ideal. Hand me the primary decomposition in terms of the combinatorics of the graph. How hard could it be? Throw all your standard combinatorial commutative algebra, algebraic geometry tricks at it. Look at, Stanley Reasoner rings, edge ideals, lead, Grobner degenerations, the lead terms, Alexander duality. You can throw as much as you want at this graph. It is not at all clear if any of those tools will be useful. But I mean, and so I guess for me, my naive optimism was dashed. Mike, actually, so full credit to one of the partners in the team. So when you're doing primary decomposition, what do you do? Well, one way to do primary decomposition, if you go back to, Cox-Little-O'Shea, is to find some polynomial that you can quotient against your ideal that pops out a piece, right? And so it turns out that if you take the, so in the matrix tree theorem, there's a polynomial which is basically the sum of over all spanning trees of it's a single polynomial. It's a sum over all spanning trees, and it turns out that when you use this polynomial to do the primary decomposition, it plays a key role. And in terms of getting the whole primary decomposition, we don't have that yet. But the amusing thing was that Mike had figured out this polynomial, but he didn't realize that it was part of the matrix tree theorem. So when I said, hey, dude, that's the matrix tree, it was very interesting to see an algebraic geometer rediscover the matrix tree theorem. So, so I think that's a good place to stop, unless anybody wants to hear a free espresso story. So yeah, I will close with this story. So here's a free espresso story. One time I was giving a talk at an AMS meeting, first talk, it was 8 o'clock in the morning. So I had some espresso prizes. I had 3 espresso prizes, and I put my espresso prizes down on the desk. And I turned my back, and at some point I turned around and glanced back, and Graham walked in. He looked around very surreptitiously, and then he picked up one of my espresso prizes and walked off with it. So don't turn your back on denim. That's I'll close with that. Thanks again.
Just be
Questions?
careful when you're giving Hal extra time.
Yeah. Oh, maybe I should tell an embarrassing. No, I'm saving my stories about Tony for the conference in this summer.
All right. Question from Alessio.
Hi, thanks for the
Hey,
talk.
Alessio.
So I just wanted to ask whether there is anything matroidal going on, because I mean, if you're using the matrix tree theorem, there might be some chance that you're actually doing something which is actually